The following is an explanation of example 5.7 off of page 199. We're given a sample of ammonia gas with a volume of 7.0 milliliters and a pressure of 1.68 atmospheres. This gas is then compressed to a new volume that is much smaller than the original at a constant temperature. Determine the final pressure of the gas. This is worded in the ideal gas law chapter, the ideal gas law section, so we're going to go ahead and look at PV equals nRT. Now, the two things that are changing in this equation are our pressure and our volume. We're told that the temperature stays the same and the number of moles is implied to stay the same. It's implied to stay the same because this ammonia is not reacting. The ammonia is not being removed and no ammonia is being added. And R is always a constant. Therefore, when we look at the initial and the final, if we were to look at PV equals nRT at both these times, this nRT, let me switch colors, this nRT and that nRT are the same. Therefore, our pressure initially times our volume initially will equal our pressure final times our volume final. Now this should be almost exactly like example 5.2 on Boyle's law. In fact, it is the exact same. I'm given my volumes in terms of milliliters. However, if I start out with milliliters and end up with milliliters, I don't need to worry about the conversion because I will be converting from milliliters to liters by dividing by 1,000 and then converting liters back to milliliters by multiplying by 1,000, and it all goes out in the end. So my initial pressure can be written out as 1.68 atmospheres times my initial volume, which is 7.0 milliliters, equals my final pressure times my final volume of 2.7. Get the pressure final by itself by dividing by 2.7. Plug everything in the calculator, and we'll get an answer of 4.4 atmospheres. As always, make sure that this is reasonable. If we are shrinking the size of our balloon, the only way we can do that is by pressing down on it. So we're increasing the pressure in order to shrink our balloon. These questions are very, very common. The trick is to always identify the constants. In this example, the constants are given all together. So PV equals nRT, the constants for this are already together, and the things that are changing are already together. In other problems, though, that is not the case. For instance, we could have the pressure and the temperature changing, or the volume and the temperature changing. If that were the case, we would need to get the volume and the temperature together, or the pressure and the temperature together, and get all those other variables on the other side of the equation. Again, this is example 5.7 off of page 199.